welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1104, Path in Zigzag Labeled Binary Tree. This is an exciting challenge that involves navigating a binary tree with labels arranged in a zigzag level order pattern. We'll break it down step by step, understand the approach, and solve it efficiently. Let's dive in. This problem involves a binary tree where the nodes are labeled in a zigzag pattern. The labeling starts from the root node, which is labeled as 1. At the first level, nodes are labeled from left to right. However, at the second level, the labeling alternates to right to left. This zigzag pattern continues, with the direction switching at each subsequent level. For example, the third level is labeled from left to right again, and the fourth level switches back to right to left. You are given a specific node label, and your task is to find the path from the root node, labeled 1, to the node with the given label. The result should be returned as a list of integers that represent the labels of the nodes along this path. To clarify with an example, consider the input label equals 14. The output in this case is 1, 3, 4, 14. This means the path from the root node to the node labeled 14 includes the nodes labeled 1, 3, 4, and finally 14. To understand this, we can visualize the zigzag labeled binary tree. At the first level, we have the root node labeled as 1. At the second level, the nodes are labeled 3 and 2 going right to left. At the third level, the labeling switches back to left to right, with nodes labeled 4, 5, 6, and 7. At the fourth level, the labeling alternates again to right to left, creating nodes labeled from 15 to 8. Following this structure, the path to 14 involves moving from 1 to 3, then to 4, and finally reaching 14. Let's look at another example where the input is label equals 26. The output for this case is 1, 2, 6, 10, 26. This indicates that the path to the node labeled 26 includes the nodes labeled 1, 2, 6, 10, and finally 26. To understand why, we can extend the zigzag labeled binary tree to the fifth level. Starting at the root labeled 1, the second level is labeled as 3 and 2 from right to left. The third level switches back to left to right with nodes 4, 5, 6, and 7. The fourth level alternates again to right to left, with nodes labeled 15 to 8. At the fifth level, the labeling resumes from left to right, assigning labels 16 to 31. Using this structure, we trace the path to 26 through the nodes as described. The path to the node labeled 26 can be summarized as starting at the root 1, moving to 2 at the second level, then to 6 at the third level, followed by 10 at the fourth level, and finally reaching 26 at the fifth level. When solving this problem, there are constraints to consider. The label is always between 1 and 10⁻6, so the solution must handle large inputs efficiently. Additionally, the binary tree must always follow the zigzag labeling rules. For edge cases, if the label is 1, the path is simply 1, since it corresponds to the root node. For larger labels, the solution must carefully compute the path while adhering to the alternating labeling pattern described in the problem. To solve this problem, we first need to understand the unique zigzag labeling of the binary tree. At the root level, which is level 1, labels increase from left to right, starting with 1. Then, at level 2, the labels reverse direction, decreasing from right to left. For example, the labels are 3 and 2 at this level. At level 3, the pattern reverses again, and the labels increase from left to right, forming 4, 5, 6, and 7. This alternating pattern continues as we move further down the tree. The challenge is to find the path from a given node, identified by its label, back to the root, while accounting for this zigzag labeling. One approach is the brute force method, where we explicitly build the tree level by level. By simulating the zigzag order, we can traverse backward from the given label to the root, keeping track of the path as we go. This approach is straightforward but computationally expensive, as it requires constructing the entire tree, even for labels at deeper levels. The brute force approach has a time complexity of O(n), where n is the number of nodes in the tree. This is because we must construct the tree and then perform the traversal. Additionally, it has a space complexity of O(n) to store the tree structure. However, this method has significant drawbacks. Explicitly building the tree is inefficient, especially for larger trees, as the number of nodes grows exponentially with the depth. This leads to high memory overhead, making it impractical for larger label values. To address these inefficiencies, we can turn to a more optimized approach, mathematical backtracking. Instead of constructing the tree, we use mathematical properties of a complete binary tree to directly compute the parent of a node. By leveraging the zigzag labeling pattern, we can derive the actual label at each level and trace the path efficiently without simulating the entire tree structure. To implement the mathematical backtracking approach, we rely on key observations about binary trees and zigzag labeling. First, we know that in a binary tree, the parent of a node at index I can be found by dividing I by 2. For zigzag labeling, the actual label of a node at a given level can be calculated using the formula level_start plus the difference between level_end and the node's index. Here, level_start and level_end represent the smallest and largest labels at that level, respectively. To solve the problem, we begin by determining the level of the given label using the formula log2, label, plus 1. Then, as long as the label is greater than 1, we compute the start and end labels of the current level, map the label to its actual index using the zigzag formula, and calculate the parent's index. We then map this index back to the parent's zigzag label, append the current label to the path, and move to the parent. Finally, we reverse the collected path to get the correct order from root to label. This approach has a time complexity of O log label because we process the tree level by level, and it uses O(1) space apart from the output path. This optimized approach has several advantages. By avoiding the explicit construction of the tree, we save both time and memory. This makes the solution highly efficient and scalable, even for very large label values. Another approach we considered is iterative simulation with parent lookup. This method is similar to mathematical backtracking but replaces recursive computations with an iterative process to calculate parents level by level. While it avoids recursion, its underlying logic and complexity are essentially identical to the mathematical backtracking approach. As a result, it does not offer any distinct advantages over the optimized method we've already described. The chosen strategy for this problem is the mathematical backtracking approach. We selected this method because of its efficiency and elegance. By leveraging the mathematical properties of complete binary trees and the zigzag labeling pattern, we avoid unnecessary computations in memory usage. This makes the solution highly scalable, with a time complexity of O log label and a space complexity of O(1) aside from the output path. These characteristics make it ideal for handling large inputs. The trade-off is that this approach is more abstract and requires a deeper understanding of tree properties and zigzag patterns. However, this mathematical rigor allows us to achieve optimal performance, making it the best solution for this problem. This problem revolves around a binary tree that uses a special zigzag labeling pattern. At the root level, or level 1, the labels increase in the usual left-to-right order, so we would see something like 1. Moving to level 2, the labels reverse and decrease from right to left, for example, 3, 2. By level 3, the labels return to the left-to-right order, such as 4, 5, 6, 7. This alternating pattern continues for all subsequent levels. The task is to find the path from the root to a given node, accounting for this zigzag labeling. The zigzag nature introduces an extra layer of complexity, as we must adjust the labels to navigate the tree structure accurately. To solve the problem, we start by understanding the tree structure. In a standard binary tree with level order labeling, the nodes on the ith level range from 2 raised to the power of I1 up to 2 raised to the power of I-1. However, in this zigzag label tree, odd levels like levels 1, 3, and 5 follow the typical left-to-right order, while even levels like 2, 4, and 6 are reversed, going right to left. The solution begins by reversing this zigzag labeling to match the standard binary tree structure. To do this, we first determine the node's level using the formula level equals the floor of the base 2 logarithm of the label, plus 1. If the level is even, we reverse the label to its normal binary tree equivalent using the formula 3 times 2 raised to the power of level -1 minus the given label. Once the label is converted to match a standard binary tree, the next step is to trace the path from the given node back to the root. Starting with the reverse label, we repeatedly append the current node to the path and move to its parent node using the formula label divided by 2. This process continues until we reach the root, which is represented by label 1. With the path now calculated in the reversed label format, the next step is to reapply the zigzag labeling. For each node in the path, if its level is even, we use the reverse formula again to convert it back to the zigzag order. Finally, since the path was calculated from the bottom up, we reverse it to get the correct root to node order and return it. The core challenge of this problem lies in handling the zigzag labeling. By reversing the labels to follow the standard binary tree notation, we simplify the problem significantly, allowing us to use the familiar parent-child relationship. In a binary tree, the parent of a node labeled x can always be found by dividing x by 2, regardless of the zigzag pattern, once the labels are reversed. The algorithm is also highly efficient. Since the height of the tree determines the number of iterations, the overall computation time is proportional to the logarithm of the given label. To implement this solution, we rely on simple and efficient data structures. A list is used to store the path from the node to the root. This list is reversed at the end to produce the final path in the correct root to node order. Beyond this, no additional data structures are necessary. The solution relies heavily on mathematical formulas for reversing the labels and calculating parent-child relationships, which keeps the implementation straightforward and efficient. Let's work through an example with an input label of 14. First, we determine its level using the formula, level equals the floor of log base 2 of 14, plus 1. This gives us level 4. Since level 4 is even, we reverse the label using the formula, 3 times 2 raised to the power of level minus 1, minus the label. For label 14, this gives a reversed label of 9. Next, we find the path in the standard binary tree. Starting with label 9, we add it to the path, then move to its parent by dividing by 2. This gives a path of 9, then 9, 4, then 9, 4, 2, and finally 9, 4, 2, 1. Now, we reapply the zigzag labeling to the path. For level 4, the reversed label 9 is converted back to 14. Level 3 remains unchanged, so 4 stays as 4. For level 2, the label 2 is reversed to 3. Level 1 is the root and remains unchanged as 1. This gives a final path of 1, 3, 4, 14. After reversing the path to get it in root to node order, we return 1, 3, 4, 14. Finally, analyzing the algorithm, the time complexity is O, log, label, as all operations, determining levels, reversing labels, and finding the path, depend on the tree's height. The space complexity is also O, log, label, as the path list stores nodes proportional to the tree's height. The provided Python code solves the problem of finding the path in a zigzag labeled binary tree efficiently. The solution is implemented in the path in zigzag tree function. Let's break it down step by step. 1. Determine the level. The first while loop calculates the level of the given label in the tree. Here, one level computes powers of 2 to find the range of each level, e.g., level 1 is 1, level 2 is 2, 3, etc. The loop continues until the current power of 2 exceeds the label. 2. Initialize path. An empty path list is initialized to store the sequence of nodes from the given label to the root. 3. Traverse backwards. The main while loop runs until label becomes 0, which means we've reached the root. At each step, the current label is appended to the path. The maximum, max_val, and minimum, min_val, values of the current level are calculated using powers of 2. These are used to reverse the label mapping in a zigzag tree. The parent node is computed using the formula max_val plus min_val label, which reverts the zigzag pattern, and then divided by 2 as in standard binary trees. The level is decrement as we move up the tree. 4. Reverse path. Since the traversal starts from the given label and moves towards the root, the resulting path is reversed before returning to ensure it starts from the root and ends at the label. This approach is efficient because it works in O, log n, time, where n is the label value, as it involves iterating through the levels of the tree. The space complexity is O, log n, for the path list, making it well suited for large inputs. The code is concise, leveraging bitwise operations for fast calculations of powers of 2, and handles edge cases like small labels, e.g., 1, seamlessly. Here, we start by importing the necessary classes and defining the solution class. The method path in zigzag tree takes an integer label as input, which represents a node in the zigzag-labeled binary tree. First, we determine the level of the given label within the tree. This is done using a while loop that increments the level variable until the value of one level surpasses the label. The one-level operation is a bitwise shift that effectively calculates powers of 2, representing the starting values of each level in a binary tree. Next, we initialize a list called path to hold the sequence of node values that make up the path from the given label back to the root. Then, we enter another loop to traverse backward from the label up to the root. At each step, the current label is added to the path. To calculate the parent label in this zigzag label tree, we first determine the maximum and minimum values for the current level using level 1 and level 1, respectively. The label is updated using the formula maxval plus minval label, which handles the zigzag ordering, and then it is divided by 2 to move to the parent level. Finally, the level is decrement to reflect this shift upward in the tree. Once the traversal is complete, the path list contains the sequence of labels from the given node down to the root, but in reverse order. To ensure the path starts at the root and ends at the given label, we reverse the list using collections.reverse path. Finally, the method returns the reversed list as the result. This completes the implementation of the path in zigzag tree method, which efficiently calculates the path in a zigzag-labeled binary tree by leveraging bitwise operations and the unique zigzag indexing logic. To solve this problem, we start by determining the level of the node with label 14 in the zigzag-labeled binary tree. The level is determined by checking powers of 2 incrementally. At level 0, 2 raised to the power of 0 equals 1, which is not greater than 14, so we increment the level. At level 1, 2 raised to the power of 1 equals 2, still not greater than 14, so we increment again. Continuing this process, we find that at level 4, 2 raised to the power of 4 equals 16, which is greater than 14. Therefore, the node with label 14 is at level 4. Next, we initialize an empty path list to store the nodes we encounter. Starting from label 14, we calculate the range of values at level 4, which is 8 to 15. Using the zigzag ordering, the parent node is computed as the sum of the maximum and minimum values in the range, minus the current label. For label 14, this results in a parent label of 9. We then divide this by 2 to find the parent node's actual position in the binary tree, which is 4. We decrement the level to 3 and add 14 to the path. Now, for the updated label of 4 at level 3, we calculate the range of values for this level, which is from 4 to 7. Using the same zigzag formula, the parent node is computed as 7 plus 4, minus the current label, giving us a new label of 7. Dividing by 2 yields a parent label of 3. We decrement the level to 2 and append 4 to the path. With label 3 at level 2, the range is from 2 to 3. Applying the formula again, the parent is calculated as 3 plus 2, minus 3, which gives a new label of 2. Dividing by 2 results in 1, the root of the tree. We decrement the level to 1 and append 3 to the path. Finally, at level 1 with label 1, we recognize this as the root and append it to the path. Reversing the path gives us the final result, 1, 3, 4, 14. Now let's look at another example, where the input label is 26. First, we determine its level by checking powers of 2. At level 5, 2 raised to the power of 5 equals 32, which is greater than 26, so the node with label 26 is at level 5. We initialize an empty path list. Starting at label 26, the range of values at level 5 is from 16 to 31. The parent is calculated as 31 plus 16, minus 26, giving 21. Dividing by 2 gives a parent label of 10. We decrement the level to 4 and append 26 to the path. Next, at label 10 and level 4, the range is from 8 to 15. Using the zigzag formula, the parent is 15 plus 8, minus 10, which is 13. Dividing by 2 gives a parent label of 6. We decrement the level to 3 and append 10 to the path. At label 6 and level 3, the range is from 4 to 7. Using the same formula, the parent is 7 plus 4, minus 6, giving 5. Dividing by 2 results in a parent label of 2. We decrement the level to 2 and append 6 to the path. Finally, at label 2 and level 2, the parent is simply 1, as we reach the root of the tree. we append 2 to the path. Reversing the path gives us the result for this example, 1, 2, 6, 10, 26. For a simpler case, consider label 1. Since it is the root of the tree, it is at level 1, and the path contains only the single node, 1. The time complexity of the path in zigzag tree function comes down to two main parts of the algorithm. First, we have the process of determining the level where the given label resides. This is done using the while one level equals label loop, which calculates the level by repeatedly doubling powers of 2 until it exceeds the label. Since the height of the binary tree grows logarithmically with respect to the value of label, the number of iterations in the loop is proportional to log 2 of the label, giving us O log label for this step. Next, the function traverses back to the root from the given label. This is handled in the while label 0 loop, where at each step, we append the current label to the result list, calculate its parent in the zigzag structure using simple arithmetic, and reduce the level by 1. Each of these operations takes O1, and the number of iterations matches the height of the tree, which is also O log label. Combining both parts, the overall time complexity is O log label. The space complexity of the function is primarily determined by the storage required for the path list. This list stores the sequence of labels from the given label back to the root of the tree. Since the binary tree has a height of O log label, the maximum number of labels stored in the path list is proportional to the height, resulting in an O log label space requirement for this part. Additionally, the algorithm uses a constant number of auxiliary variables, such as level, max_val, and min_val, which collectively require O1 space. These variables do not scale with the size of the input. Therefore, the overall space complexity is dominated by the path list, making it O log label. When comparing this approach to a brute force or naive method, we can see a significant improvement in efficiency. A naive approach might involve constructing the entire zigzag-labeled binary tree up to the required level and then tracing the path. This would result in O2 to the power of h, time and space complexities, where h is the height of the tree, which is proportional to log 2, label. The exponential growth arises because the number of nodes doubles at each level of the tree. In contrast, the current approach avoids constructing the tree entirely. Instead, it uses arithmetic and bitwise operations to calculate parent-child relationships directly. This optimization reduces both time and space complexities to O log label. Mathematically, this is supported by the logarithmic growth of the tree height with respect to the label. Since all operations in the algorithm are performed either once per level or in constant time, the algorithm achieves logarithmic performance. By directly calculating the parent in the zigzag structure, it ensures efficient traversal without unnecessary overhead. Let's start by addressing some of the common mistakes that can occur when working with zigzag-labeled binary trees. First, misunderstanding the zigzag traversal pattern is a frequent issue. Many people assume it's just about alternating directions of node visitation, but the labeling often follows specific patterns, like odd and even levels being labeled differently, which can easily lead to incorrect traversal or outputs if not properly understood. Another mistake involves incorrect parent-child relationships. In unconventional labeling schemes, such as zigzag, it's easy to miscalculate these relationships, especially when the labels are reversed. Careful mapping between levels can help avoid these logic errors. Memory inefficiency is another pitfall. For instance, some solutions use multiple queues or stacks unnecessarily, which increases memory usage. Instead, you should aim to optimize by reusing a single data structure and reversing nodes in place when needed. Off-by-one errors also crop up frequently, especially when calculating label ranges for specific levels. Using the correct formulas, like 2 to the power of the level, can help ensure that these boundaries are accurate. Lastly, don't overlook edge cases. Scenarios like single-node trees, empty trees, or very deep trees often reveal hidden bugs. Simulating these edge cases during testing is crucial for a robust solution. Now let's consider some insights that can help you excel in interviews. Recognizing patterns is a vital skill when solving binary tree problems, especially those with zigzag traversal. For example, odd levels might follow one direction, while even levels follow another. Visualizing how labels or indices shift across levels can make these patterns easier to identify. Mathematical insights are also crucial for unconventional labeling schemes. Specifically, understanding the relationships defined by powers of 2 can simplify your approach. For example, pre-calculating level boundaries or deriving formulas can help you navigate the tree more efficiently. Interviewers also tend to emphasize optimization, so it's important to aim for solutions with O(n) time complexity and minimal space usage. Avoid redundant structures whenever possible. Additionally, if you choose to use extra data structures, like 2 stacks, be sure to clearly explain the trade-offs involved. For instance, you might prioritize simplicity in implementation even if it increases space usage slightly. Being able to articulate these trade-offs demonstrates a strong understanding of both the problem and your solution. Finally, let's look at some related problems and alternative approaches that can expand your understanding. For related problems, LeetCode 103 focuses on binary tree zigzag level order traversal, which is directly linked to this topic. LeetCode 102 explores standard level order traversal, while LeetCode 429 extends this concept to n-ary trees. Another interesting problem is LeetCode 662, which deals with calculating the maximum width of a binary tree. For alternative approaches, the 2-stack method is a popular choice. This involves using 2 stacks to alternate traversal directions, pushing child nodes in reverse order when switching directions. While this simplifies the logic, it does increase memory usage. Another option is the deque-based approach, which uses a double-ended queue for efficient node insertion and removal from both ends. This method is more memory efficient than 2 stacks but requires careful handling of insertion order. Lastly, there's in-place reversal. This approach processes nodes level by level, reversing the order in place for odd levels. It minimizes memory usage but can make the implementation more complex, especially for large trees. Each of these methods has its pros and cons, so understanding their trade-offs will help you choose the best approach for a given scenario. Great job completing this problem. To summarize, we tackled zigzag level order labels in a binary tree using an efficient mathematical approach. We discussed the key concepts, complexity, and the thought process behind the solution. Thanks for joining, and see you in the next video. Keep coding and growing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!